Hello and welcome to day 9 of the Advent of Code 2021. My name is Jacob and I will walk you through the Kotlin solution that I implemented for this day and show you around how I arrived at it. After a quite rocky day 8 yesterday, this one was not necessarily easy, but in my opinion a lot more straightforward again. So once again, as with every day, I will first explain, not read, but explain what the puzzle of today is. If you already are familiar with that, please use the chapters below to skip ahead straight to any of the solutions. Right, then I would say let's get going. So the idea of this puzzle today is that you need to try to find low points in this input here, which is a height map. So what this would mean is that, well, these are like your x and y coordinates, and then each of the digits is essentially how high the peak of this point is, or maybe rather the valley. I'm not sure how to interpret it. It's rather a valley because we need to find low points. So what I pulled up here, because this is, if you would think about how this would look in real life or in 3D at least, it's pretty much something like this. Like not for this exact input, but the idea is like this. So each of these cells is one index. So you just literally have like this, and going down are one of these cells, and then the digit in there is how much is the z-axis, right? How much it goes down, up and down. So all of these would be zeros, right? Because they don't go up and down anywhere. But then the more red or blue it gets here, you might in this case have positive and negative values. So in this case there's only positive ones. So imagine that this goes only up or down, however you want to interpret it. But this is essentially the value. So this would be like a 9, for instance. And here we would have, well, a 0 or and here then something negative. So what we need to do in the first part right here is to find all of the low points in this input. So it's nicely labeled here, actually. Ignore saddle point, but these minima are precisely what we're looking for. So of course we have one global minimum somewhere that is like the lowest we can go, but we also have these local ones, right? So in this puzzle, the first part, we essentially have to find all local minima. We just have to find all the lowest points in the input, which might be also the lowest in the entire grid, so to say, but it's not required to be that. So in the first example here, this is pretty straightforward. The way to nicely find this is to like go over all of the grid, and at every step try to see, is like, am I, so to say, the digit you're currently looking at, am I the lowest ones compared to all of my neighbors? And in this case, the important thing here is discards diagonal neighbors. So it only looks at like the direct ones horizontally and vertically. So an easy way to see, am I a low point, is just, hey, am I the lowest one compared to all my neighbors? So in this case, it is the case. 1 is lower than any of the neighbors. So we know this has to be a low point. Imagine, if this doesn't make a lot of sense, imagine it for any other number. So for 3, for instance, if you check, hey, am I the lowest compared to my neighbors? You see like, no, 2 is lower. So this definitely is not a low point. And then you already see how this works. Is that now you do the same thing for 2, and again you see, no, 1 is lower. So you can, with this technique, also move closer and closer to the next closest low point, or even the global minimum of the whole map, so to say. Which is in essence how a gradient descent works, if you're familiar with it. Well, not quite, because you don't calculate any gradient, but it is like a hill climbing in reverse, a valley climbing, I guess. So you try to go like closer and closer, step by step, and to the bottom until you found it. Not required in the first part, but keep this information in mind. So in the first part, we just need to find the low points in general, not necessarily how to get there. So what we can simply do for that is, what I said here. So we just scan each time and see, am I the lowest compared to my neighbors, and then we know it's a low point. Final thing we need to do is get a risk level for each of the low points, which is simply just calculated by 1 plus the height, so the value. So the risk level of this low point would be 1. It's 1 plus 0, so that's 1, or this one would be 6. And then we just sum all of them together. In this case, it's only 4, and they give some value, and that's our puzzle result, our output. Let's check out the code right now. again, as I do usually, I modeled all of this in classes because I don't really like it if it's not type safe, as you probably already gathered if you watched any of the previous episodes. So the first thing is I created a grid class that accepts a nested list of integers, which is just like, well, yeah, the mapping that you receive. So, well, we can open it here actually. Just this whole grid essentially. So this would be one of the outer ones. Sorry, like these are all the outer lists essentially, and then these are the nested ones. So you have the y and x axis. And then it generates, well, it hides away this fact behind this class. So what we then do, first step right here is, well, let's actually first look at parse input. Parse input, very straightforward in this case. We already did this for day 5, I believe, pretty much the same. So we split by a new line such that we get each of the, well, lines. Then we split by empty string again, filter out as we have to do oftentimes already, if it's not blank. If you're not familiar with this, the reason is that if you have an empty string and you split by it, you will also get like the beginning of the string and the end of the string, which is just like nothing, it's just empty. So we need to filter that out. So we say filter, it is not blank, because afterwards, if we coerce this into an integer, you cannot coerce empty string into an integer, so this would throw an exception. So afterwards, what we simply have is our nested list of int. That is pretty straightforward. Then we pass this right here into our grid and save into a variable. What does the grid do internally? Let's close these for now and look at them in a bit. The grid creates this matrix. So the matrix is literally the same, but instead of having an integer in here, it has a bit more rich and also more type safe cell, not just the raw value. What is a cell? A cell has, well, the value that it actually holds, which is the integer, but it also is like self-aware of sorts in two ways. So first of all, it knows its own coordinates. So coordinates is literally, as you see here, just x and y. But what it also knows, it knows which grid it is part of. Why is that? We'll see in a moment. So what we just simply do here now is when we're generating the matrix is, so we call this here in the, to get this matrix field, we in an indexed way map over all of our outer lists such that we know, okay, this is the y coordinate. That's important here to note, right? If you parse it in this way, x and y are swapped around, then you would usually have it, right? Because these are like the outer lists, like this and this and this and this and this, which is, you see if I do this right here, that's the y-axis actually, and then the nested ones are the x-axis, because there you go like from left to right. So it's the other way around, then you would usually have a coordinate system, just important here. So that's the y, that's the x. So the outer one is a y, and then we also get each of the nested rows. We do the same again over that, also indexed, such that we again get the index, which is our x, and the actual value at that cell. So then we can just construct the cell by giving it ourselves, so to say, and this referring to the grid, obviously, the value of the cell and the x and y coordinates. There's a constructor then here that for us makes coordinates out of x and y and then constructs the cell right here. Right. Then we have the matrix. So that is that. That's pretty much all we do to just get the grid itself. And then what we can now do is this can be solved a lot easier. And I figured I'll show you directly the way I did it like this, because I figured it's anyways required for part 2. So the way you could have also solved this instead of doing that is literally what is described here in the puzzle. So you just iterate over each of the cells and check, hey, am I the lowest compared to all my neighbors? If yes, you count up some counter, or you return true or something like that, and then count all the trues or sum them together. That works, perfectly fine solution, but since anyways for part 2 we need something else, let's check it out, because it's required to understand anyhow. So what I wrote then is the grid has, in this case, an extension function called getLowPoints. So this would return you, yeah, well, literally all the low points. So in the end, once we have them, we can literally just say, hey, sum me together the value of the low points plus 1, which is this formula that was given here. So once we have, in this case, 1, 0, 5, and 5, we sum them together while also adding 1 to each. And then we literally return that. That's part one. But let's check out what get low points actually does. So, and here now, the other functions you saw in the grid maybe already get interesting. I made this as an extension function, a private one, since I figured from a software design point of view, this is not really like part of the grid, right? This is like just a use case how you could use the grid. So personally, I wouldn't put it as a function in the grid. Obviously for this thing, specifically because it's nested inside of my day 9 object, it's not like you can use this grid anywhere else nicely. I mean, you can, but it's not really helpful. But you see what I mean, maybe like finding low points is not really the job of just a generic grid of values. The other reason why I did this is that I kind of have the feeling that I probably need this again in a future puzzle, in which case I would put it somewhere in a shared package or something. And then it becomes more apparent, because then we can reuse this without having it cluttered with like a bunch of methods get low points that we only need for this puzzle, but that make no sense in the context of a general grid anymore. So that's where I draw the line, where I think that using extension function is a bit cleaner, because then you don't clutter up your namespace. Because then if you do like grid dot and then it will show you like everything, sure, in this case it's not a lot, but you get the idea. If you have like 100 use cases, then at some point you have very many methods that you might only need in very specific situations. It's a bit of a trade-off, or case-by-case decision, of course. Right. So what does this do? We get all of the cells of the grid. Very easy. You can get all the cells by just flattening the whole matrix. So if we just like flatten all the cells in the inner list together with all the other lists in the in these, then we just get all the cells. And then what we can do is map over that, and for each cell try to find its closest low point. And this function is now the actual like interesting one in this well, there's one other one that you'll see in a second in this puzzle today. So how this works is precisely what I described earlier with the gradient descent or hill climbing or whatever you want to call it. So what we do is we try to step by step ask like each cell, hey, what is like your closest low point, right? So let's maybe go back here. So let's say we're I don't know, here. We ask the 7, hey, what's your closest low point? It will respond obviously with 6, because from all its neighbors that's the closest, the lowest. And then recursively we can keep doing this. So then we ask 6, because now this refers us essentially to, hey, ask 6, like that's my closest low point. So we ask 6, hey, what is your closest low point? It will tell us 5. And now we reach the base case, which obviously is what you need for a recursion. 5 asks itself, or whatever, the grid, hey, what is my closest low point? And then we receive answer, it's yours, you are the closest low point, at which case we stop the recursion, we reach the base case, because we know, hey, this is it. And then of course this propagates back, this bubbles up the stack again, such that 7 or 6 is told, hey, your closest low point, like actual low point, lowest you can go, is 5. And again, it bubbles up here, and such that the 7 then knows, hey, my closest low point is this 5 at this position. Which is precisely how you would do this here in a gradient descent, right? If you're here and you want to know where's my closest low point, you ask your neighbors, they say blah, 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 and then you like over time recursively walk closer and closer into the valley here. If you want to know more about it, if you're not familiar with this concept, yeah, that's called hill climbing, or well, in this case, you're not climbing, but you get the idea. There's various ways to do it. This is probably the most straightforward one. So what all we do right here is we have a base case, the first if condition, and our recursive case. To do this, we get all the adjacent cells. Let's ignore for a second how this is calculated, so we can focus on this. I will obviously still cover it in a moment. So all the neighbors. And then we simply say, are all, like, for all the neighbors, am I, so this dot value, so we're in a cell right now, right? Am I lower than any of the other values of my adjacent cells? And if this is true, we know that this is the lowest point for all the neighbors. So we just return this because this is called get lowest point, closest low point. And if we are our own low point, we're obviously also our closest low point. The other thing obviously of this is that if we are like currently in a recursion already, this would then, as I said, bubble up to whoever originally started this chain. And then in else, we just get our local minimum, so to say, from our point of view, from our neighbors. So this is pretty straightforward. Just say, hey, from my adjacent cell, which is the minimum value that you can offer, and then we get a cell back. And then we do what I just described on paper. We ask again that cell, that local low point, hey, give me your closest low point. And you see at the side here, this is recursive, so this then would do what I described. It would ask further and further until it found it, and then all the way back inform the original requester, so to say. And then we can know for all of them what's the closest low point. If this doesn't make sense, drop me a comment, please. I'll make sure to elaborate a bit more. It's maybe difficult to wrap your head around. And also we're gonna run this now so you see what's happening. One note here. This is obviously runtime complexity wise not very nice. Like if speed or memory consumption or whatever would be a factor in an actual system, this is not how I would typically do it, because the problem of course with this approach is that if we do this for every single cell in our grid, and you can see right here the grid is large, I mean still runs pretty fast and doesn't use a lot of memory, but you get the idea. It's not super trivial. You waste like a lot of CPU cycles doing the same stuff over and over, right? If you are, I don't know, here and you try to find the lowest closest low point, you do like 5 4 3 2 1 0 or something like this. So you walk like that. But then if you later on in the next row ask the 4 here, you do the same or part of the steps again. You again do 3 2 1 0, right? So you do many of these recursive cases again and again and again. One way, of course, of doing this is having some sort of cache in an easy way, such that if you already know, hey, this specific cell by literally just a hash map or something, some form of memoization. So if we know already, if we calculate in the past, hey, this cell's lowest nearest neighbor is this one, that you look it up in your memoization cache. This would be a nice improvement for that. Then you could even keep this and just add a cache. So for some languages, you can literally here say, I don't know, memoization. Something. There's probably a nice way to do it in Kotlin. I don't know it by heart, but this is what I do to improve it. Although this would obviously work fine like this, and honestly it still runs within a second or so. But it is important to keep in mind. Right. The thing we haven't checked yet is get adjacent. And there you might also now notice that why the hell did he put like diagonally false with a default of false? Wasn't even asked for, right? That is true. I figured in the first part, hey, probably because it's specifically mentioned in part 1, specifically mentioned, only consider like vertical and horizontal neighbors. And I figured, in part 2 we definitely have to do diagonal ones. So I immediately from the beginning build it in a way. I mean, you could argue this is just plain stupid. I cannot disagree with you. I figured, hey, I will just directly build it in a way that it will support diagonal ones, because I'm not building these for speed. I anyway start quite late into the day of solving them, so it's not like I can make any leaderboard or whatever. So it's not the goal at all. So I figured, let's build it like that directly. And you'll see, let's say, in a moment if this turned out to be useful or not. I haven't unfolded this part 2 yet. You'll see in a moment. But on paper, it is supported by doing the following. And now let's check out get adjacent. So this is where it becomes important that the cell knows what grid it is part of, because as you can see right here, this referring to the cell also has a get adjacent method that asks the grid, hey, based on my own X and Y coordinates that I have saved here for myself, what are my like adjacent cells? And then this returns a list of cells. So this is a nice way of like just by having a pointer, a reference to a cell, finding out what its adjacent cells are. Of course, the other way you could do this is get adjacent and then pass in the grid here, but then here you also need to receive the grid and pass it in at the beginning, and you just always like drag around this grid object or the reference to it, which just makes the code quite ugly. So I figured this is a nice way. This is private, so you cannot access it from the outside. It's just that the thing is a bit more like smart, so to say, the cell object, and it's a bit more contained and self-aware, let's say. It knows its own coordinates, knows its value, and it also knows which grid it is part of. And since all of these are vals, so immutable, once you have constructed this, there's no way of messing it up, like overriding the coordinates or saying, oh, you're now part of another grid that doesn't even match the coordinates anymore. So I think it's a pretty nice, nifty way of doing this in a type-safe manner. Right. So what we simply do, we ask the grid, hey, based on my coordinates that I know, what are my neighbors? And again, of course, we have to drag along this diagonally flag here if we check diagonal ones or not. So let's check out this one, and then we're already done actually, because generate matrix we already took a peek at. So to get the adjacent ones, you literally just have to do some like index lookup in the matrix right here. So we're given, hey, what are the adjacent ones of this x and this y coordinate, and should I do this diagonally or not? So all we now do is literally say, and this is where I think Kotlin becomes quite nice in handy with this get or null method. So we say to get like the one on top of me, give me the y index that I myself, the cell, so to say, is -1. So what we would get here, let's say we're the 7 right here. We would say we want to start with this. So what I did is I go clockwise. So I say I start with this one, then I do this and this and this and so on and so forth. Or of course, if it's not diagonally, only this, and then at the right side and the bottom and so on. So for the 7, we simply say, give me the one that's like a y index less than myself. So which would leave us here, right? Remember y like this, obviously. And where my x index is the same as myself. So yeah, it's on the same x, but on a y one less. So the important thing here is that 0, 0 is here, which might be a bit confusing because in regular coordinate systems, it's of course here. So if you would want to have it like a coordinate system you know about, then you would have to flip everything around. Not necessary here, so I didn't do it, but just to keep that in mind. And then I will not walk through all of them, but that's literally how you resolve all of the other ones. And then the thing that is really nice here about this get or null is that it avoids this annoying thing that you would usually have when working with matrices, that you always have to check, oh shit, am I at the edge? So if you're an 8 and you want to know your left-hand neighbor right here, so this would be this one, usually would have to say, if my x -1 is smaller than the like, if it's outside of bounds essentially, so here there's nothing here, right? So if you would just access it without any safety in place, it just throws index out of bound exception. So usually you would check, hey, is it smaller than that? Really nice, and Kotlin has this get or null. So if this is a valid index in this case nested list right here, then you get whatever is there. So in this case a cell, and if not, you get a null. And with that in mind, we just here at the end do list of not null. So this is the same as saying list of and then filter out, like here filter not null. This is literally the same. It even says now here, hey, this is not necessary, it's already non-nullable. Such that it automatically ignores for us everything that doesn't have a neighbor on some side. So for the 8, this would resolve to null, so it doesn't appear in the list, meaning that the 8 only has the neighbors 9, 7, and 7. Which is, I think, a really nice and clean solution to get this without doing any annoying if statements. The only if statement that we do have, of course, is if it's diagonally. So what I do here is I also resolve that, same logic, but if this wasn't wished for, so if this would be false as the default here, then we just say null, so else null, meaning that it is just not appearing in the final list, since obviously just as any non-existent neighbors, the nulls are filtered out. So I think this is a nice and clean way to get this. And obviously, as you notice here, this is also in clockwise order. So this is the top one, this is the top right, this is the right, and so on and so forth. And then we get a nice clean list of all the adjacent ones, automatically taking care of any ones that don't have like some neighbor on the side because they're on the edge of the grid. Right. And then with this information here in mind, we can get the closest point. And then what we simply have to do as the last step, and I'll run this in a moment, is once we have the low point of each cell, we just say dot distinct. Obviously, this is, again, runtime complexity wise, kind of a waste of time. You might as well do the thing that I described in the beginning, because obviously you will have quite some duplicates in here because many have a shared closest low point. So if you do distinct, you have the true like lowest points in this grid, and then at the end we literally just do this summation here with the value of all of these. So that is how part 1 works. Let's quickly look a bit at how this looks inside of it, because I think there's a lot of stuff happening here, so this would be a bit confusing otherwise. If it's completely clear to you, you can skip ahead to part 2 in this video, and we take a look at that. So the grid would be looking like that. So we have the matrix, and this would be the first row in the grid right here. Then we have all the cells in here. You see they have a reference to the grid, and now you can also see obviously that this is this doesn't need any more memory since it's just reference. So you see here this has hash code 876, or the reference 876, just as the outer grid itself. So this and this is the same thing, meaning that this is just like a pointer in essence. So it doesn't need any extra memory. The same could have been done with the coordinates. Those are duplicated, but since we don't have duplicate coordinates, that's not a concern. And then we have the value right here. So this is how our input looks like. You see this just goes up here all the time, the x value, and then once we drop into the next row, y goes to 1 and the same as well. Right, that's that. Now let's take a peek at this recursive function, because that's really the meat of it, as well as the get low points. So if we put a breakpoint here where we get all the low points, and if we evaluate just what is here, this is what it looks like. Keep in mind this is quite a lot, because obviously you see our input is pretty large, so there's a lot of low points. But this is just all of them now. So you see these are typically very low values. Sometimes you have like a bit of a higher one, but apparently then this is just the lowest for all of its neighbors. And that's how we get those. Now let's also, because this is the interesting part really, let's try to see how we get for one cell. So let's say we take grid dot cells, and this obviously is this because it's an extension function, dot first. So we just get the first cell, and here say give me the closest low point. Then there's apparently, as you also saw here already, happens to be a 4 at coordinates x2 and y1. I mean, we can quickly have a look here. So this is at x2 and here, and at y1, so this one. So this would tell us that the first cell, meaning 0, 0, this is its closest low point. And then let's quickly walk through how this would recursively work. I'm not going to do it in debugger because it's a bit annoying to step through. Well, actually, you know what? Why not? So you see here indeed the cell that we're trying to find its closest low point of this, because again, it's an extension function on cell, is indeed 0, 0, our 9 right here. The adjacent cells are 6 and 8, which is true. You see now also that it automatically discarded the ones that are not there because it doesn't have any other neighbors. If we would have said diagonally false, true, we would also got the 7, of course. And now we see it's not this, because a 9 is not lower than either 8 or 7. So we go into the other case right here. So let's jump there. So the local low point of here is a 6. Obviously, out of 8 and 6, 6 is lower. So we continue with that. Let's now I'm going to step further such that we get into, because it calls itself, right, into the recursion case. So now we do the same with 6. We see its adjacent cells are 5, 7, and 9. 5, 7, and oh well, the 9 we were just at. It's also not the closest one, the lowest one, but of course the 5 is. So if we continue, let's remove this one because it's the same, obviously. We get to this 5. This time it's 6, 4, and 6. 6, 4, and 6. Now we move down, right? Because 4 is lower. And now you see how this works. So we always step like one step at a time and just climb, or descend in this case, closer and closer to the bottom. Now we are at 4, and from here we actually now get into the base case, because you see all the other values are 5, 6, 5, and 7. So here we could have also said, hey, what's the lowest point, and then realize it's myself, instead of doing this all others are lower. Sorry, I'm lower than all others. This would have also worked. Actually, maybe that's a bit easier to understand. Well, so now you see if we go here, it should go into the base case, which indeed it does. And then of course we like bubble all the way up again, such that then we know, okay, from the original 9, the 4 is the lowest. And that's part 1. Let's move to part 2, which, with this in mind, is fairly, or actually very easy to solve with one like nice idiomatic Kotlin trick. So what we need to do in part 2 is try to find basins. So if you would imagine, this is very visually can be done nicely again, these things. We need to find all of the basins. So if you would, I don't know, put a marble here or some water, I guess is a nice example, where it would like logically collect. So if I would let it rain here, the rain would obviously collect in these 2 basins, and maybe behind this there's also a basin here, a bit hard to see, it does look like it a bit. So in this example right here, we would need to rotate it to be sure. We have 3 basins. We have the one that's hidden behind here where some water would collect, this one and this one. So we have three basins, and these we need to find, right? There's many ways to do this. The nice, in my opinion, easy ways, if we already have the setup I showed you right now, is to simply do the following. So all I'm doing in part 2 is I say generate the grid again, give me the cells of the grid. Now there's one thing that is important here before we can do the actual cool thing. It mentions here that somewhere the number 9 should be like ignored. Yeah, locations of height 9 do not count as being in any basin, because they're like sort of like the floor, if you would consider like that, because you go low, of course. So 0 is the lowest, so you only go down. So what you see in here, what is like the 0, the green color, is sort of the 9 in our case. Otherwise everything would be a basin, right? Like this would all count as a basin because it is technically also low. So you have to discard all of those, which I do by here. So I say for all my cells, if its value is a 9, then filter not filtered out. And now comes the cool part. We can group by every cell's closest low point. And that's literally all we need to do, because that will give us a map of all the low points as the keys, mapped to what other cells are part of that basin. So we have like all of the basins keys are the actual low points, and then the values is a collection of all the cells that are part of that basin. And of course there's a cutoff point at some point. So you have let's maybe go in the example right here. So at some point there's the cutoff. So this one probably still counts to this basin, because like technically the water would slope in this direction, but then the one on the other side here already counts to the other basin. But the nice thing, of course, is what we just need to do now, or what the code does for us, is if we do our gradient descent right here, or our climbing or descending, we get precisely that. So if we start from this cell and say, hey, where's your close low point, and do our our stepping like down, we automatically arrive at this one. And if we do it with the one that's a bit behind this saddle point, actually now the term comes into use, on the other side of the saddle point, we automatically see, hey, this is a bit higher than I am. So I'm going to go into the other direction and go behind this hill here. Meaning that if we group by, so group by meaning we create a map that everything that shares this one will be collected into a collection right here. And that's precisely what happens under the hood. So if we say every single cell in the grid, sort yourself into a map such that you map yourself to your personal closest low point, we get like all the basins. Again, this obviously is like runtime complexity wise not ideal because you have to do this for every single cell recursively. Again, here the memorization would be perfect. But then you get precisely what we want. So discarding all the green ones here because they're like the 9s, so to say. If we ask this cell, hey, where's your closest low point? It would say like the one here in the bottom, or maybe let's do it with this, easier to see. So you ask this cell here, it says, hey, it's this. If you ask this cell here, it will say, yeah, it's also this. If you ask that cell here, it will also say, yeah, it's this. So if you group by this characteristic, automatically the basins form, because this will be the key, and everything else would have told you within the iterations, hey, this is my personal closest low point, such that each basin is now nicely a key value pair in the map. Let's obviously run this now such that you see how this would look like. Right, so we have our basins right here. So we have 206 basins apparently. It's a lot more than in the examples on the website, but yeah, this is just simply again because the matrix is pretty large. Right, let's check the first one, which is again our 4 here. So this is the 4 we already looked at. So you see here coordinates x2, y1. It's this 4 here. This is apparently, well, not apparently, we knew this already, is a low point. And now we see that its basin has 23 size. Oops, not the key, but the value. So somewhere in here, there's itself is obviously part of it. That's important. So here you see the same 4 with coordinates to 1. And also you would see that, again, here the reference is 1055, which is the same as the key. So itself contains itself in the basin, obviously. Then you have all the other values in here. So let's try to find like a quite high one in terms of x or y. So maybe this one here, value 8 at coordinates 5, 1. So we go 5 to the side, 0, 1, 2, 3, 4, 5, and 1 down. So this 8 right here. And then you now see that it is actually surrounded by 9s, which is the floor, so to say. So here's a 9, there's a 9, there's a 9. Meaning that it is definitely part of the basin that goes into this direction. So it would be nice to highlight this in some way, maybe also build that, let's see. But you see how this would happen for this one. So if we now do this for everything, it automatically collects, like it all clusters it together around this. And if at some point obviously there's a cutoff of some sort, either because there's like a 9 or because there's something else that is also higher but not necessarily 9, and on the other side it would like descend towards something else. And then you have all your basins just as you see on this picture, even though it's 206. Yes, and not just 3. So this is how this would work, simply by asking each cell, hey, what's your close low point, and then grouping them together by that. And then the final thing we need to do in here is, if we go to the puzzle again, we need to get the 3 largest basins and multiply their sizes together. Very easy, obviously, in Kotlin. We just take the values. We don't really care about the keys, so the actual low points, but yeah. Take the values, sort them descendingly by their count. So these size values right here, such that we get, the thing sorted descendingly. We take the first 3, that's literally what it said there. And then I added an extension function similarly to sum of, that is called product of. So we just multiply all of them together by, again, this size value. So product of, we can quickly look at it, but it's very uninteresting. So it just starts obviously with base case 1, so to say, and we fold over all of the elements with the selector and multiply everything and then return. It's literally the same as sum of, but with a multiplication operation instead. Yeah, and then if we do that, we arrive at well, obviously a large number because it's multiplied. And that is our output for part 2. Right, this was part 2 of day 9 of the Advent of Code. If you have any questions about anything, don't hesitate to drop a comment below. I'm very happy to answer them. Also, something I want to point out is I do have a Discord server to keep in touch with you, answer questions, have some discussions or whatever. So if you're interested in that, consider joining there as well. You'll find the link to that in the description or on the channel page itself. Apart from that, thanks a lot for watching. Consider subscribing to the channel for more videos like this one. I'll make one for all the other days, if I can solve them. And I see you tomorrow on the first 2-digit day 10. Tschüss!